You know, the periodic table is quite fascinating. I mean, the design of it, the structure, the ordering, everything that goes into it. And then there's all kinds of interesting little trivia with the naming of things. And sometimes it's just fun to look around and find, some things and look up like their names and stuff like that. And like, oh, here's a new one. I didn't notice this one before. The element of surprise. In this video, I'm going to talk about investigating chemical compounds. Now, in this next generation lesson 3.1, it's got a lot of information in there, so I'm going to break it into parts. So in this part here, part 1, I'm going to talk in particular about ionic formulas and covalent bonds. So let's get started. Now, what is a chemical bond? That's what this whole thing is about. Well, it's a lasting attraction between atoms that enables the formation of chemical compounds. So these are chemical bonds that associate atoms with each other. Now, before I get into explaining chemical bonds, in particular ionic bonds, I want to go back to something that we learned before. In modeling atomic structure. In the lesson that I talked about modeling atomic structure, I went over some vocabulary, and that was related to things on the periodic table. We talked about metals. The metals are good conductors of heat and electricity, where nonmetals are elements that are usually poor conductors of heat and electricity. And then we talked about the metalloids or semiconductors, and these are the intermediate conductors of heat and electricity. There are 6 of them, and they're located on the stair-step line. And if you guys recall, in that prior lesson, I wanted you to understand where these things are located on the periodic table. So let's take a look at that right now. So at our periodic table, we have to the left, these are our metals. All the metals to the left of the stair-step lines, that's the stair-step lines. These are the metals, these are good conductors of heat and electricity. And to the right are the nonmetals, poor conductors of heat and electricity. And on the line, we have the 6 semiconductors or metalloids, which is these guys right here. So I wanted you guys to understand that on the periodic table, so I'm going to be talking about that when I talk about ionic bonds right now, because an ionic bond is generally between metals and nonmetals. So it's a bond between something on this side of the periodic table to something on this side of the periodic table. Metals and nonmetals make ionic bonds. The bond is formed by the attraction between oppositely charged ions. Now, the other types of bonds are going to come up in this lesson that we're going to talk about is covalent bonds. These are generally between nonmetals and nonmetals. So if you have nonmetals bonding with nonmetals, these are covalent bonds. So things bonding with each other over here, that would be your covalent bonds. And this is formed when atoms share one or more pairs of electrons, and we'll get into that in a bit later. Now, if we have metals bonding with metals, these are called metallic bonds, and I'll talk briefly about that in the next lesson. These are metals between metals are metallic bonds, and they are basically what you have here is many electrons. It's called the free electron model. You have many electrons around a positively charged ions. So when you have metals, you have the metals turn into are ionic, positively charged, and the electrons are free to move about it. That's why they're good conductors of heat and electricity, by the way. Okay, so predicting ionic charges. So we're going to talk about ionic compounds, but first we have to be able to predict ionic charges. Now, if you guys recall from prior lesson, we talked about the different families of the periodic table, and the last family here on the right was the noble gases. The noble gases are the most stable electron configuration. And so to predict the charge of an atom when they become an ion, they will become an ion to get the most stable ion they can get will be in an electron configuration of a noble gas. So, what is the easiest way for magnesium, here's magnesium, to reach a noble configuration? Should it gain or lose electrons? So we've got magnesium here. It could gain electrons. It could gain 1, 2, 3, 4, 5, 6 electrons and become noble gas configuration of argon, or magnesium could lose 1, 2 electrons and get a noble gas configuration of neon. So the easiest way for magnesium to get a noble gas configuration will be to lose 2 electrons. And so if you lose 2 electrons, magnesium's charge becomes positive 2. Now think about it. If you lose 2 electrons, it becomes positively charged. Why? Because now you've got 2 more protons than you had electrons. You're losing negative, which gives it a positive charge. A lot of students get confused on that. Let's go in the other way. What's the easiest way for sulfur to reach a noble state? Would it be to gain or lose electrons? So here's sulfur right here. Would it be easier for sulfur to gain 2 electrons to become argon's configuration? Or would it be easier for sulfur to lose 1, 2, 3, 4, 5, 6 to get neon's configuration? Well, it's easier to gain 2. So therefore, if you're gaining 2 electrons, remember electrons are negative, then sulfur would become -2. So these superscripts, you put a superscript, the number, and a positive or a negative. If it's just a shift of 1, if it's you don't have to put 1 positive or 1 negative, you just put plus or minus. But if there's 2, you put a 2, or a 3, a 3. When ions become positive, they are not called cations, they're called cations. Remember, they're ions, so let's just keep that ion part there, and we're just going to add cat in front of it. Cations that have a positive charge include cesium, lithium, potassium, rubidium, sodium. Some positive 2 positive cations are barium, beryllium, calcium, magnesium, strontium, and aluminum would be a 3 positive charge. But you don't have to memorize that. You use your periodic table. So if you take a look at all the 1 positive cations, cesium, lithium, potassium, rubidium, sodium, they're all right here. Lithium, sodium, potassium, rubidium, cesium, and francium. They're all in the first column, because in the first column, again, it's easier. Remember, noble gas configuration is the most stable configuration. So in the first column, it's easier for them to lose 1 electron. So all these lose 1. 3 becomes 2. 11 becomes 10. 19 becomes 18. They're all losing 1 to get a positive charge and become a noble gas configuration. If you take a look at the 2 positive ones, they're in this column here: beryllium, magnesium, calcium, strontium, barium, radium. These are all positive 2, so this list is not inclusive of everything. And they lose 2, so 4 becomes 2, 12 becomes 10, 20 can get to 18. So if they lose 2, they can get a noble gas configuration. And aluminum over here is actually positive 3. You look over here and you might think, well, it's going to go to 18 and gain 1, 2, 3, 4, 5. Nope. Aluminum, it'd be faster to lose 1, 2, 3. 13 is closer to 10 than it is to 18. So aluminum does become positive 3. So you should be able to look at the periodic table and predict the charge of elements. You don't need to memorize the charge that they'll be, but look at a periodic table. You should be able to predict them. All right. The next type of ions are anions. Anions are negatively charged ions. And when they're put in an ionic formula, the name changes. So fluorine becomes fluoride when it becomes ionized. Chlorine becomes chloride. Bromine becomes bromide. Iodine becomes iodide. So you take off the last part of these names and you add IDE. So if you're looking at chemicals and you see that it ends in IDE and it's an ionic compound, you know that that's an anion. Okay, so we go there, and here's some examples of the charges: 1 negative, 2 negative, and 3 negative. Now let's take a look at our periodic table and where they're located. The 1 negatives, fluorine, chlorine, bromine, iodine, they're all located right here. So this right here, these are the halogens, by the way. They gain 1 electron to become stable. So 9 to 10, they're all just 1 away from stability of a noble gas configuration. And so all of this column will be -1, or just a negative charge. This column here will be 2 negative. So that's oxygen, sulfur, selenium. These will gain 2 electrons to become stable. And finally, nitrogen and phosphorus would gain 3 electrons to become stable. So an ionic bond is a bond formed by the attraction between oppositely charged ions. So let's make an ionic bond here. Sodium and chlorine. When sodium becomes an ion, it's positive, chlorine becomes negative, and these opposites attract, and that's what makes the bond. It's like magnets. When they attract, they make the bond. Now you have to remember, sodium can't, losing an electron makes sodium stable, and when chlorine gains an electron, it makes it stable. But in order for something to lose an electron, something else has to take it. We don't have electrons floating around in our, just in our air right here. So chlorine wants that electron, but where's it going to get it from? Well, sodium will donate it. And so when sodium donates it, it becomes positively charged. Chlorine becomes negatively charged. They both get noble gas configurations. They both become more stable. And in the process, though, because one's positive and one's negative, they stick together like magnets. That's the idea behind an ionic bond. So let's write the formula for aluminum fluoride. Here's another ionic compound, aluminum fluoride. Remember, it's fluoride, which would mean that the base element was fluorine. So we list the elements, or the symbols for each element. So if you look at your periodic table, take a look at it, and you should be able to predict that aluminum is 3 positive and fluorine is -1. If we take a look at our periodic table here, aluminum is located here, and we could have aluminum. Was it be easier for aluminum to get to 18 or to 10 if it's 13? So we know 10 is closer to 13. It's 3 over, so that's why it becomes +3. And if we take a look at, what was the other one on there? Fluorine. Fluorine is right here, number 9 to 10. So that's why fluorine's -1 and why aluminum is 3 positive. So let's go back to our situation here. So you should be able to predict the charge. So practice that. Make sure you can look at the periodic table and predict the charge of any of the elements when they become ions. And remember, you always get to use a periodic table. It's like a calculator. It's a tool to help you solve problems. You don't need to memorize the periodic table. Okay, so number 2, write the symbols with the cation first. You always put the cation first. The positively charged one is always first when we write ionic formulas. So we write them together with the cation first. So aluminum and then the fluoride, which is 3 positive and the negative. And then you find the least common multiple. The least common multiple of 3 and 1 is 3. So 3 goes into 3 for aluminum. 3 goes into 3 once, so there's 1 aluminum. And fluorine, 1 goes into 3 times. So this right here means that you have 1 aluminum and 3 fluorines. It takes 1 aluminum to 3 fluorines to make this stable. Let me try to illustrate this visually for you guys. Some people get it right away and that's no problem, but some people struggle with how to do this. So this is what I'd like to show you guys, what's happening here to make it rather make a little more sense to you visually. So we're going to talk about aluminum fluoride, and again, we look at our periodic table. We find that aluminum is on the periodic table and it needs to lose 3 electrons to begin a noble gas configuration, and fluorine needs to gain 1. Now what I'm going to do visually here is, if it's going to lose 3 electrons, let's make arrows. It's shooting off 3 electrons. So it's shooting off 1, 2, 3 electrons. It's giving away 3 electrons. And in the process, fluorine needs only 1 electron to be stable. So if you take a look here, 1 aluminum and 1 fluorine is not going to make a stable situation here, because aluminum needs to get rid of 3 electrons. But where there's 1 fluorine, there's going to be billions more, and so they're going to have more fluorines. They're going to be happy to accept those. And so if we take a look at this now, this stable situation, we have for every 1 aluminum, it took 3 fluorines to neutralize it. And so what happens is they stick together like magnets, but you're going to have 1 aluminum with 3 fluorines associated around it. So this subscript 3 represents that there's 3 fluorines. And so that's how we would write aluminum fluoride. Let's do some more practice. Let's give this one a shot. Magnesium sulfide. Look on your periodic table and you find magnesium is right here, number 12, and 12 gets to 10 easier than it does to number 18. So therefore, it's going to be a positive true. A lot of times students will just, you can have your own periodic table and print and write on it. A lot of times people write plus 1 here, or plus here, 2 plus, 3 plus, it's just negative, 1 negative, negative 2, I'm sorry, 2 negative, that'd just be negative, and 3 negative. This column here could be 4 positive or 4 negative, so it could go either direction. Anyways, so magnesium is 2, so we're going to write that charge here. Magnesium is 2 positive, and sulfide is sulfur, which is right here. It's in this column here, so this is 2 negative, which gaining 2 electrons here to get to, it would be a stable situation here. So sulfur would be 2 negative. And if I illustrate this again, by the way you would do this mathematically, the way it's kind of taught in a textbook, is the least common multiple. Least common multiple is 2, and each one goes into 2 once. But let's just illustrate this again, like I did last time, and you'll kind of see what's going on here. So magnesium gives off 2 electrons, but sulfur accepts 2 electrons. So it's actually a perfect match. It's a 1-to-1 ratio, so it's just magnesium and sulfur. So that's the formula. Magnesium sulfide is just MgS. Let's try another one, aluminum oxide. Aluminum, look on your periodic table, has a charge of 3 positive, and oxygen has a charge of 2 negative. So when we do this one here, we would have aluminum, and remember, aluminum always has to get rid of 3 electrons to be stable. And oxygen has to accept 2 electrons to be stable. So this isn't okay. It's not stable. Aluminum needs something else to accept that electron. So if there's one oxygen available, there are millions of oxygens available. So we have another oxygen here. And oxygen, though, remember, always accepts 2. You always have to have 2 in a 3 ratio. So it's accepting 2. So this oxygen needs more electrons. It's not going to be a stable situation. All right, well, there's 1 aluminum. There's millions of aluminums, so that will give 1. Uh-oh. But now aluminum's giving off more electrons. So we're going to put another oxygen here and accepting those electrons. And now everything's balanced. Everything has worked its way out. So if we take a look here, we have 2 aluminums. So we put a 2 here. And we've got 3 oxygens. 1, 2, 3. So aluminum oxide's formula is aluminum 2 and oxygen 3. Another trick you can do is, and this is what most people do, is you take these charges and you cross them. So you put the aluminum and you put this charge, the anion's charge at the aluminum's subscript, and you pick the oxygen and you take the aluminum's charge as the subscript. So take a look at that. Just cross the charge, you get the same answer. However, you do need to reduce it, because let's take a look at this one here. If you were to do that here, cross these charges, you would have written magnesium 2, sulfur 2. And that is not the appropriate answer. It's a 1-to-1 ratio. So if you do those charges and you can reduce it, you need to reduce it. Metal, nonmetal makes a salt, which makes an ionic compound. Ionic compounds are salts. So anyways, and they make a crystal lattice. Now, when we do that, we see these ratios of like aluminum chloride, where it's 1 aluminum and 3 chlorines. What that means is the ratio of the relationship in the crystal structure it makes. So a crystal lattice is the repeating symmetrical arrangement of atoms. So here's an example of a crystal lattice of sodium chloride. And when you do this, sodium's positive and chlorine's negative, so you just have a 1-to-1 ratio. But it's not just a sodium and a chlorine together, it's a crystal. And that crystal is just a pattern repeating sodium chlorine over and over and over. So that's why we reduce it, because it gives us the idea of what the ratio is in the crystal lattice. The crystal could be large, it could be small, so we don't know exactly how many sodiums or how many chlorines are in the crystal itself, so we reduce it to its lattice structure. So take a look here. What I'd like you to do is pause the video and try to answer these questions. So what I'd like you to do is number a piece in your evidence notebook, 1 through 7, or 1 through 14. The first 7, write the ionic formulas for the following ionic compounds. So in these 1 through 7, write the formula for them. So the formulas look like what's on this side of the paper. And then in reverse, see if you can name these. Can you name these properly? And these are always written with the ion, or the cation first and the anion. But you remember when you name them and you look on your periodic table, you have to take off the end of the word and add IDE. All right, so pause the video here and try to finish this up. Try to work on this, and then we will be back and we're going to talk about covalent bonds next. When we do covalent bonds, we show what they look like, and this what they look like tells us a lot about the behavior of these molecules. So to figure out what they look like, we're first going to start off with something called a Lewis structure. And this is a model that shows how the valence electrons are arranged among the atoms in the molecule. So doing a proper Lewis structure will help us answer some questions that's going to come up later on. When we do this, we follow the octet rule, and that's except for the 1s orbital. So 1s, that's just hydrogen and helium. They don't follow the octet because to be stable in the first period, they only need 2 valence electrons. But everything else, all the other nonmetals, are going to need 8 valence electrons to become stable. That fills up both the s and the p. So besides helium and hydrogen, they only need 2. All right, rules for writing Lewis dot structures. First, sum up the valence electrons for all the atoms in the molecule. So the first step is you take a look at the molecule, all the different atoms, and you write the sum of all the valence electrons for the atoms. Now, valence electrons are the outermost electrons, so it's not all of the electrons total, it's just the outermost electrons, because it's those outermost electrons that are interacting with each other to make those bonds. Number 2, use a pair of electrons to form a bond between each pair of bound electrons, or atoms. So a bond is a pair of electrons that will connect all of them together. So you take all of your atoms and you connect them with bonds, and that's going to count for 2 of those valence electrons. Now, once everything's connected, arrange the remaining electrons to satisfy the octet rule. So these are the rules. But now let's take a look at what a Lewis structure actually looks like. So here we have hydrogen and another hydrogen. Now hydrogen has only 1 valence electron, but to be stable, it would need 2 valence electrons. That would be the helium configuration of 2. So to be stable, it needs another electron. Now, unlike ionic bonds, an ionic bond, remember, it loses an electron to get stable. Well, if the hydrogen lost an electron, that wouldn't make this one more stable. So they both want an electron. So what they end up doing is they share these electrons, and by sharing, they create a bond. So this line here represents 2 electrons. And so this hydrogen has 2 electrons around it, like helium. And this hydrogen has 2 electrons like helium, and they're both stable like helium, except they're stuck together because they're actually sharing. This one's got 2, and this one's got 2. It's like a Venn diagram. They're sharing that commonality, and they're stuck together. So hydrogen forms stable molecules when it shares 2 electrons. So the proper structure for hydrogen is H2. We write a H2 for hydrogen. Now, let's do it with fluorine. Fluorine has how many valence electrons? So let's take a look at that right now. Fluorine, how many valence electrons does fluorine have? Well, fluorine is located right here. And another thing that we talked about before in the periodic table is valence electrons. And you should remember that everything in this column has 1 valence electron. This column has 2 valence electrons. 3, 4, 5, 6, 7, 8, except helium has 2 valence electrons. And you might already have these numbers written on your periodic table, just a refresher on what those numbers mean. Fluorine has 7 valence electrons, so what we're going to do here is write those 7 valence electrons around the fluorine in the form of dots. So we're going to use each side, because remember it's the rule of octets, so we have 4 sides to a square, and so if we have 4 sides and each has a pair, that will account for all 8. So we've got 2, 4, 6, 8 total possibilities around there. And since fluorine has 7, we're gonna have one side with only 1 electron. So it's got 1, 2, 3, 4, 5, 6, 7 valence electrons around there. And fluorine, to become stable, would be neon's electron configuration, which is 8. So fluorine needs 1 more electron. And if there's another fluorine around it, it also needs another electron. So what do they end up doing? Well, this 1 electron that is deficient needs another pair here. They will share with each other. And so when you see fluorine in nature, it's always F2. So if fluorine could share an electron with something else, it would have a full set. Sharing an electron between 2 fluorines creates a covalent bond. So this is the covalent bond here, and it's the sharing. So this fluorine again has 8 electrons around it, and this fluorine has 8 valence electrons around it, and they both have a noble gas configuration, and they're both quite stable at this point right now, and they have a covalent bond between the two of them, a single bond, by the way. Okay, so let's write the Lewis structure for water. First thing we do, this is step 1. Remember, we're looking at those steps. We sum the valence electrons for H2 as shown. So in step 1, we're going to sum. This is what it meant. So hydrogen has 1 valence electron and oxygen has 6 valence electrons. Look where oxygen is on your periodic table to determine where that charge is. So water has a total of 8 valence electrons, 1 from 1 hydrogen, but there's 2 hydrogens. So they each give 1, and then the oxygen gives 6. That's where this number 8 came from. The next thing you do is you connect everything together. And as we connect things together, those are the bonds. So we have the H connected to an oxygen and another H connected to the oxygen. And so we've connected it all together. So note that a line instead of a pair of dots is used to indicate the pair for bonding electrons. So right now we've used 4. There's 2 electrons here and 2 electrons there as well. Now we're going to distribute the remaining electrons to achieve a noble gas configuration. So hydrogen only needs 2 electrons around it to be helium configuration. So this hydrogen is already stable. It's got 2, and this hydrogen's got 2. But the oxygen only has 4. It's got 2 over here and 2 over here. But we've used 4, and we had a total of 8, so we've got 4 left over. And if we put those electrons around the oxygen, now the oxygen has 8 around it. So this hydrogen has 2. It's got these 2. This oxygen has 8. It's got 2, 3, 4, 5, 6, 7, 8. And this hydrogen also has 2. So all these have a noble gas configuration, and this would be the Lewis structure for water. Okay, let's try again. We're going to do the Lewis structure for carbon dioxide. Carbon dioxide is a carbon and 2 oxygens. So carbon, look on your periodic table. Make sure you can do this. Look on your periodic table, and you find that oxygen has 4 valence electrons because it is we just look at the S&P block for valence electrons, and if you go across, it's 1, 2, 3, 4, you find hydrogen, and oxygen has 6 valence electrons. We add up the total for carbon dioxide. We have 4 plus 6 plus 6. Remember, there's 2 oxygens. Each of them are contributing 6. So we have 16 valence electrons. We form a bond between the carbon and each oxygen. So when we do organic molecules or carbon-based molecules, the carbon is usually the anchor point, the center. So we're going to put whatever the first element is usually the center of it. So carbon dioxide, we're going to put that in the center. So we put the carbon in the middle, and we connect everything together. So we had 16, and we used 4 in these bonds. There's 2 here and 2 here, and that gives us 12 left over. Now the next job is to place the remaining 12 electrons to achieve a noble gas configuration for all the atoms. So if we have 12 electrons here, let's take a look. Did I place 12? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So is this correct? Well, at first glance, you might think it's correct, but in all actuality, no, it's not correct. So whenever you're done with your Lewis structures, I'm going to show you how you can double check that if you got it correct or not. Is this correct? First thing I want you to check is, did we use the total number of electrons? Remember, we had 16 electrons. Did we use all 16? Well, let's take a look. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Did we use all 16? Yes. If you didn't, then it's not correct Lewis dot structure. There's another thing you have to check. The second step is the octet rule for each atom. Does each atom have 8 electrons around it, except for hydrogen only needs 2? So oxygen has 1, 2, 3, 4, 5, 6, 7, 8. That one does. Let's look at the carbon. It has 1, 2, 3, 4. Carbon does not have 8 electrons around it. This is not stable. And this oxygen here has 1, 2, 3, 4, 5, 6, 7, 8. So this is not stable because the carbon only has 4. Here's another representation of carbon dioxide. Let's see if this one's correct. Did we use 16? 1, 2, 3, 4, 5, 6, 7, 8. 9, 10, 11, 12, 13, 14, 15, 16. By the way, these are called double bonds, and we can also have triple bonds. So we did use all 16. The oxygen has 8 around it. 1, 2, 3, 4, 5, 6, 7, 8. The carbon has 8 around it. 1, 2, 3, 4, 5, 6, 7, 8. And this oxygen has 8 around it. 1, 2, 3, 4, 5, 6, 7, 8. So this is the correct structure for carbon dioxide. This one is not the correct structure for carbon dioxide. Some people have a hard time like, well, how do I know what to do, and just kind of figuring it out like that. But that's kind of the textbook way to do it. The way I like to do it, I call it the connect the dots method. And there's 3 steps to connect the dots. Now you can do whatever way you want to do it as long as you get it right. So the first step to connect the dots is write the Lewis structure or write the Lewis dots configuration for all of the atoms in your compound. So don't put it all together yet, just for the atoms of your compound. And I'm going to go through these steps with you. But these, and give you an example of how this works. The second step is pair all lone electrons with a line. So all the lone electrons, you draw a line connecting them, all the while singing the Connect the Dots song. Yeah, you actually sing in this part. Make sure all atoms are connected. The first atom listed in the compound is normally the center atom. And what you might be wondering right now is, what is the Connect the Dots song? Well, the Connect the Dots song is by this gentleman here. Is an old TV show called Pee-wee's Playhouse. And what he would do is he'd throw a bunch of dots almost every episode, and he'd connect the dots, and he'd always sing this song, and it's a brilliant song. So if you know the song, sing along with me. But let's listen to Pee-wee sing it first.
Connect the dots, la 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 la. Connect the dots, la 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 la. Hey.
And that's the whole song. And we will sing that. Well, I'll sing that. And then you have to redraw a clean version, because what this is going to look like, it won't be a very nice looking representation. But I'm gonna do this with you guys right now with carbon dioxide. The first step is to write the Lewis dot configuration for each atom. Remember, just the atom. So we've got carbon. And remember, carbon should be in the center. Remember, the first thing, step 2, is the center. And then we've got 2 oxygens. And I'm going to purposely just kind of place them wherever. It doesn't have to be, I mean, it's kind of straight, but you could do it any way you want. Now, carbon has 4 valence electrons. So we're going to put those 4 dots around first. So 1, 2, 3, 4. Remember, electrons are negatively charged. They don't want to be near each other. So they're going to find areas apart from each other before they pair up. So they have to go apart before they pair. So you have 4 lone electrons on carbon. Oxygen, on the other hand, has 6. So let's take a look at what this looks like. We go 1, 2, 3, 4, 5, 6. Notice these guys are paired. Paired is good. We want everything to be paired. Let's do it again for this oxygen. 1, 2, 3, 4, 5, 6. and we're going to pair these ones as well. So I'm purposely made this, it's going to look pretty ugly, but that's okay. I want it to be ugly for this first example here. And now the second step is to connect the dots while singing the Connect the Dots song of all lone pairs. So I circled the paired ones. I'm not connecting dots on these paired ones, just the lone pairs. So we got to make sure everything connects together here. So we're going to go like this. Connect the dots, la la la. Connect the dots, la la la. Connect the dots. All right, so purposely this is an ugly mess, but now the third step is to write it clean. So let's write this clean. We've got oxygen here, and I've got two lone pairs on the oxygen. So I'm just going to write, I could write it where it is, like that, but I could also write it somewhere else if I wanted to. I just got two lone pairs, and then it's connected to a carbon. It's connected 2 times, so we're going to put a double bond there. And then there's a carbon. There's no lone pairs around the carbon, but the carbon's got 2 bonds, 1, 2, 1, 2, to an oxygen, which has another 2 lone pairs. So I'm going to put those lone pairs here. I could have put it somewhere else, but what I could not do is put this lone pair in between the bonds. The bonds have to be, I can't put these, see this one's on the left side here? I couldn't put those electrons here because that's where the bond is. That would imply that there's more electrons in between the carbon and the oxygen. So this should be moved around to make it clean. This is the clean version, and by the way, that's the same answer as what you got on the other one. I find that when you do connect the dots, it just works out. It's pretty simple. So let's try some more connect the dots. Let's try some more Lewis structures. We're going to do this with nitrogen, an hydrogen, and an oxygen. So remember, the first one should be the center. So we got nitrogen, we got an oxygen, we got our hydrogen and an oxygen. Hydrogen has 1 valence electron. Nitrogen has 7 valence electrons. Maybe to look on your periodic table, make sure you can figure that out. So 7. 1, 2, I'm not 7, 5. My bad. Nitrogen has 5. 1, 2, 3, 4, 5. I probably should have looked at the periodic table, not done that off the top of my head. I wouldn't have said that wrong. So it's got 5, and oxygen has 6. So 1, 2, 3, 4, 5, 6. If they're paired, I'm not going to connect those dots. And now I've got to connect everything here. So let's go. Connect the dots. La, la, la. Connect the dots. La, la, la. And now write it clean. We got hydrogen to nitrogen, 1 bond to nitrogen. Nitrogen has a lone pair, and then it's got 1, 2 bonds, 1, 2 bonds to oxygen, which has 2 lone pairs. And if you would have written it like this, that would be fine as well. That would be fine. But do not write it like this. Don't do this. See how that's there? This part here, that's a no-no. So don't write it that way. Okay? Let's try another one. We'll do carbon and 3 chlorines. Now, when you're handwriting in chemistry, it's useful because to make the lowercase in cursive so that we can see that that's a carbon and a chlorine that's a lowercase. The first letter is always capital, so if there's a lowercase, that would, so otherwise some people might think that there's a carbon and another carbon and 4 iodines if you were to write it like this. CCI. That might look like a carbon, and an iodine. So that's why I do it in cursive, and it's just a common practice. So center is carbon, and we have 4 chlorines. And I'm just going to use my paper. Don't be afraid to use the paper, space stuff out. Carbon's got 4. 1, 2, 3, 4. Chlorines have 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Remember, I'm not going to connect the dots with these ones that are already paired. Now, let's connect the ones that are lone to be paired. So connect the dots, la la la. Connect the dots, la la la. So we got this monstrosity. You do not turn in papers like this to your chemistry teacher. You got to write it clean. So let's write this clean here. So we have a, let's go over here. We have a carbon, and the top one is connected to a chlorine. So I'm going to go up to a chlorine, and the chlorine's got three lone pairs. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 3 lone pairs, and then the one on the left is connected to a chlorine with 1, 2, 3, 4, 5, 6. 3 lone pairs. The one on the bottom is connected to a chlorine with 3 lone pairs, and the one on the right is connected to a chlorine with 3 lone pairs. So this would be your answer. And you get questions on tests and stuff like that. You might get this on a test or a quiz. This right here, this chlorine and carbon and 4 chlorines, and the questions might say, so you just have this, and a typical chemistry question might say, how many lone pairs are in this molecule? And so you have to draw the Lewis structure, and then you can count lone pairs. Lone pairs are not these are bonded pairs, and these are lone pairs. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've got 12 lone pairs. That would be something that could be asked with CL4. How many lone pairs are there? It could ask how many single bonds are there? You'd say 4. How many double bonds are there? None. How many triple bonds are there? None. So you wouldn't know that just from looking at this. You'd have to actually draw it to figure out what the answer to that would be. So let's do one more. 3 carbons and 6 hydrogens. So 3 carbons, 1, 2, 3, and 6 hydrogens, 1, 2, 3, 4, 5, 6. Each hydrogen has 1 valence electron, so we'll just put 1 dot on all of those. And the carbons each have 4 valence electrons. None of these are lone pairs. They're all single electrons. Everything needs to be connected together. Now, what's important to note here is don't connect the dots between 2 hydrogens, because if you do that, they're done. They can't associate with the rest of the picture. Everything here has to be connected. It all has to be connected together. So let's give this a try. Connect the dots, la la la. 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 All right, we got it. So let's draw this clean now. We've got a carbon, and on the top I have a hydrogen, so don't curve it like that. Got a hydrogen. On the left I've got a hydrogen. On the bottom I've got a hydrogen. To the right I have a carbon, and this carbon on the bottom has a hydrogen, and to the right it's got another carbon, and it's connected to that carbon 2 times, so it's a double bond. And then to the right of that one we have a hydrogen, and to the bottom we have another hydrogen. And if we take a look at this, we've made an octet for all the carbons and hydrogens on here. We have this carbon's got 1, 2, 3, 4, 5, 6, 7, 8. This carbon's got 1, 2, 3, 4, 5, 6, 7, 8. And this carbon's got 1, 2, 3, 4, 5, 6, 7, 8. And because we put the proper dots in the first time, we know we have all the electrons. We didn't have to add it up and do any math or something like that, like the other example, like the kind of the textbook way of doing things. So that's the connect the dots method. If you want to add it up and do the math, that's fine as well. You just have to get the right answer to it. So let's take a look back at our lesson here. And what I'd like you to do is do the Lewis structures for all of these 12 right here. So pause the video right here and see if you can answer these 12. and we'll get together and share answers with each other, and I'll answer any questions you guys have. Good luck, and I'll talk to you soon.